guys. Right, so we'll do a quick register and then we're gonna get back on with this past paper. So, if you could all comment your names, if you're here, that would be great. Yeah, I got it. I got the mic. Hang on. Where are we? There we are. So, I've got Lucas. Lucas, where were you on was it Wednesday? Yeah, I don't remember you being around on Wednesday. Have you caught up on stuff since? Emily, yep. Ruben, also Ruben, I think you were away on Wednesday. Make sure you catch up on anything that you missed. Finn, yep. Amy, Oliver, Isla, Eliza, Tom, who I think, Tom, you were away on. Did you email? Sorry, I don't remember that. Tom, I think you were away as well, so catch up on stuff. And I think Harry and Sally came to my lecture this morning, so it's just Ben that we're missing. All right, cool. So yeah, on Wednesday we were looking at this past paper, which we're going to continue on with today. Cool. So yeah, I'm just going to get you guys. So again, I'll give you a minute. You guys try it, and then I'll go through it as an example, and we'll just make our way through these papers. Were you there, Tom? I can't remember if I swiped you. Maybe you were a bit late start. I don't know. I'll have a look in a minute. Okay, so for the first question, it's 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 marks. So I'll give you guys 11 minutes to give it a go. Cool. Oh, that's fine. Comment if you need any help, and comment when you've got a correct answer. Cool. Right, get started. Do you guys want do you guys want a bit more time because of all the lagging and connection issues? I think I sorted it out now, but I can because you guys commenting part A and part B, so I might give you a little bit longer. Another what, 6 minutes. You got a bit of time today, yeah. 6 more minutes. See if you can get through them. Nice. Okay, yeah, let's do that again. So there's three options you can have for this one. Well, we need to state two of them, so we'll go through all three. Number one is that trials are independent. If trials are independent, well, we got to link that to the question. So we can say trials, what we really mean is the probability each time the dart hits the target is independent of each throw. So the probability is the same, in other words, um, for each throw. So throws are independent. And we can say fixed probability of hitting, no screen over there, hitting target. Cool. The other one is a fixed number of trials. So I guess you could say only 10 throws in there as well. Okay, next bit. Find the probability h is greater than or equal to 4. So I'm going to write this out as a distribution. H, binomial distribution, number of trials 10, probability success 0.1. And we're trying to find the probability h is greater than or equal to 4. So if I bring up the calculator, and we are looking for a binomial, BCD, lower is going to be 4, upper, big number of trials 10, probability of success 0.1. Oops, left that too early. And execute, and we get probability 0.0128. Cool. Okay, next bit. Okay, for each child, the random variable f represents the number of the throw on which the dart hits the target. Cool. So it could hit it on the first throw, second throw, fourth, fifth, whatever. We want to find the probability that the child hits it on the fifth throw. So to hit it on the fifth throw, the child must have missed it the first, second, third, and fourth throws. So we need the probability of a miss, which is 0.9 to the power 4, and then we need a hit 0.1 on that fifth throw. And it has to be that order because it has to happen. There's no point rearranging this one. It has to be that last probability has to be a 0.1. So we have to have 4.9s first before we have the 0.1. So if you times all that together, you'll get 0.0128. Cool. No, you won't. That was the answer to the last bit. I've looked at the wrong thing. If you times that together, you should get 0.0656. Okay, so next part is where it gets a little bit more difficult. Okay, so Thomas assumes that in this experiment, no child will need more than 10 throws. So he thinks 10 is the maximum any child will need. And he instead models the probabilities using the equation written there. Right, so what we're going to do is draw a table because this is a discrete random variable. So we're going to put all this in a table. So we're going to have n in the top of the table. And well, I'm going to need more room than that. N in the top of the table and P F equals N in the bottom. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10, whatever. That is not an 11, it's a 10. Cool. Right, so we'll fill this with our probabilities. So our first probability is going to be 0.01 plus n minus 1. Well, n is 1, so it's just going to be 0.01. Next one, if we put in that, we're going to get 0.01 plus n minus 1. Well, n is 2 this time. 2 minus 1 is 1, so we're going to get 0.01 plus alpha. The next one will be 0.01 plus 2 alpha, and so on and so forth. And the last one, the 10th one, will be 0.01 plus 9 alpha. Okay, so the way we're going to find alpha is if we add up all of those probabilities, it should equal 1. So in other words, we can say the sum of p f equals n should be 1. And you'll notice that this is actually an arithmetic series. So our first value is 0.1. Our next value is 0.1 plus alpha, then plus 2 alpha, plus 3 alpha, etc., etc. So it's an arithmetic series. Remember the sum for an arithmetic, n over 2, 2a plus n minus 1 d. God, that's annoying. There we go, n minus 1 d. Our first term is alpha. Sorry, our first term a is 0.01. Our common difference is alpha, and we know there are 10 terms, so n is 10. So the sum we are told, well, the sum has to be 1 because we're summing probabilities. So 1 equals n over 2, so that's 5. Lots of 2, lots of 0.01 plus n minus 1, well, that's going to be 9 lots of d, which is alpha. Cool. So if we expand that, we get 1 equals 0.1 plus 45 alpha. So 0.9 is 45 alpha. And if you divide that, we get alpha equals 0.02. Right, last bit. Last couple bits even. Find the probability f equals 5. So we want to try and find this one here. So the probability at f equals 5 is going to be 0.01 plus 4 lots of alpha, and alpha is 0.02. So we're going to get 0.09 for that one. Right, and the last bit, explain how they differ in describing the probability that the dart hits the target in the experiment. Well, who was it? Peter's model thinks that the probability is the same. Every single time, probability is constant. Whereas Thomas's model thinks that you start off with a probability of 0.01. Every shot you get slightly better, and that it's certain that you get it at the end. So main thing here, Peter's model assumes hit probability is constant. So Peter assumes constant probability. Whereas Thomas assumes probability increases with each throw. Cool. Right, that's that one done. So, next question, guys. If you could try that skipped question there. If you guys could try this one. So this is the kind of the beginning bit of stats. Hopefully you can see that. Yeah, it's quite small, but have a look. So we got this is all the beginning of stats that we started with last year. Finding alpha should be more than 4 marks, you reckon? Oh crap, wait, we did that one. I've skipped too many. I don't know, it's just writing a table out, putting stuff in a table, doing arithmetic. Maybe I'd give it 5, but it's not much harder than that. Yeah, so we're going to try this one. Yeah, give it a go. If there's a bit you can't do, skip it and move on. I would like you guys to try and get through all this though. So 6, 7, 8, 9, 10, 11, 12, 13 marks. I'll give you 13 minutes to do it. And this should cover all the beginning bit of stats that you've probably forgotten from last year. So do what you can, comment your answers when you got them, and ask if you need help. But it should all be easy stuff if you can remember it. All right, let's go through this one. So, part one, what sampling method is it? It is opportunity sampling, which Tom got. Yeah, good. Opportunity sampling, good. State and describe an alternative method. Well, we could use quota sampling. And they could, there's a few different ways you can talk about this, but you need to describe it. So they could split employees into age quota and fill these quotas as people arrive at work. Cool. Okay, Taruni decided to ask every member of the company the time it takes them to travel to the office. State the direction process, the selection process she used. Well, that would be a what's it called again? Census. Okay. Write down the interquartile range for this data. Here's the next one. So if we zoom in, I think we got 26 to 58. So that's a 32 interquartile range. Calculate the mean and the standard deviation. Well, forget rid of all this. Mean is going to be sum of x over n. So that's 4133 over 95. And sigma would be the square root of 202,294 over 95 minus 4133 over 95 squared. And if you do that, you get your mean as 43.5. And your sigma is 15.4. And really for all these, we should put minutes as a unit. Min, min, min. Cool, good. So I think you guys, from what I can see, all got that so far. Part F. So this is a bit more difficult. Which measure of spread and location would you choose? Well, because we've got those two extreme values, the two outliers, those are going to drag up the mean and drag out the spread, whereas the median is the middle value. So the median doesn't know how extreme those values are, neither does the interquartile range. So interquartile range and the median, so Q2 and the IQR are better. Let's just say they're not affected instead of better. Not affected by extreme values or outliers. And because our data has outliers and extreme values, they're a better choice. Okay, and the last bit. So we got talking about people's journeys to work there. So Rana journey from work changed from 75, so it was here. It's now changed to 35, so it's now changed to there. And David's journey has changed from 60, which was there, to 33, which is now there. So the question is, what's that going to do? It's going to change her box plot. How's it going to change Taruni's box plot? Well, let's have a look. Remember, the quartiles kind of split the data into four. So you got Q1, Q2, Q3. So the lower quarter of the data is lower than quartile 1. And that's not changed. There's no new data below it. So Q1 stays the same. Q1 remains. Q2, Q2, the median. Well, we've now got more values below the median, so that's going to shift the median and make the median a lower value. So Q2 gets lower. If we've got more data beneath Q2, the middle value is going to be a new lower value than it was. And same with Q3. We've got two values that have gone from above Q3 to below Q3. So that's putting again more data below Q3. So Q3 gets lower. The greatest value and the least value are unaffected, and the outliers are unaffected as well. Cool, that's it. All right, let's move on. Next question. This one's pretty tricky, to be honest with you guys. I think we might have done it before, but just be careful with this one. So normal distribution. I will underline one key bit is that Alice's calculator requires 4 batteries and will stop when any one battery reaches the end of its lifetime. So remember that, but give it a go. 14 marks. Comment if you need any help, and then we'll go through it. Sorry guys, I got distracted at there. Cool. Okay, yeah, so this one is quite difficult. Let's have a look. So, what am I doing? Yeah. Okay. So, part one of this one isn't too bad. So just find the probability any battery will last for longer than 16 hours. Okay, so we've got a normal distribution. L is normal with a mean of 18 and a deviation of 4, so 4 squared in there. We want to find the probability x is greater than 16. So if I bring up the calculator, where are we? There we are. Normal distribution this time. So our lower value there is going to be 16. Upper, something big. Sigma is 4 and mu is 18. So let's draw that. Have a look. Okay. So we get a probability of 0.691 for part A. Cool. So that's part A. So 1 mark here, nice and simple. Okay, now it starts to get difficult quite quickly with this question. Is it not 17 because it's greater than? No, because it's a normal distribution, remember? And normal, you're thinking of binomial there, Ollie. With normal, you could be 16, you could be 16.000001. You know, we want all of that to be shaded in. So we just do greater than 16. So because it's a continuous, because normal distributions are continuous, we don't need to go greater than. You're thinking binomial. Anyway, so yeah, we got that one done. At the start of the exams, she puts in 4 new batteries, okay? And she used her calculator for 16 hours, but she has another 4 hours of exams to sit. Ooh, so you've got to find the probability it's not working. So in other words, we'd want to try and find the probability that the calculator lasts for longer than 16 plus 4 is 20 hours, given that the calculator has already lasted, or the battery has already lasted for more than 16 hours. So you want probability L is greater than 20, given L is greater than 16. And the way we're going to do this is with the formula. So we know A given B is A and B out of B, like that. So if we turn our equation into a similar thing, we're going to get the probability of greater than 20 given greater than 16 is the probability of greater than 20 and greater than 16 divided by the probability L is greater than 16. Okay, but the numerator there, greater than 20 and greater than 16, well, if it's greater than 20, it's going to be greater than 16. So we don't actually need to have all of that in there. We can just get rid of the second half of this fraction, and this is what we're trying to find. The probability L is greater than 20 divided by the probability it's greater than 16. And we've already done part of that. We got the denominator from our answer to part A, so we're going to get 0.691 on the bottom. All we need to do is find greater than 20. So if I go back on my normal distribution, go up to the top, I'm just going to change the lower bound now to 20, and we get 0.3085. So 0.3085. Cool. And if I divide those two, we will get 0.44621. So that is the probability of a battery lasting longer than 20 hours given it's lasted more than 16 hours. Cool. But we got 4 of those batteries, so we need to do that to the power 4. So brackets to the power 4 because there's 4 different batteries, and our answer ends up as, run out of space here, 0.308. Wait, no, I'm not done it. Divide those two together, and we get 0.0396 as our answer. No, it's not greater than or equal to because equal to doesn't make any sense on a normal distribution because it's continuous. So the probability of equaling something is 0. So it makes no difference on a normal. Zero point zero 0.0396. Cool, is everybody okay with that? It is a bit tricky doing the whole conditional probability with a normal distribution. But there we go. And it's hard as well thinking, well, oh, we got 4 batteries, we've got to times it by, put it to the power 4. Anyway, okay, now it gets even more confusing. So, oh, I shouldn't have got rid of that. Hang on. Let me recall what we just did. Okay, we're going to need the 0.44621. So that's the probability of the calculator. The probability for a battery greater than 20 given greater than 16 was 0.44621. Okay, now I can get rid of it. Alright, so sadly Alice only has 2 new batteries, so she can't actually replace all 4. So she's going to replace 2 of them, so that's going to give us 2 of the 0.44621 to the power 2. And then she's got 2 brand new batteries, and the brand new batteries we only need to last 4 hours. Okay, so we can do probability x is greater than 4. Find that on the calculator. So again, if I go exit, go back up to lower, make lower 4, and work it out, we get 0.9997 9998, I guess, let's say. So that's going to be the probability of the 2 new batteries dying before 4 hours, so 0.9998 to the power 2. And if we times all that together, that accounts for all the different batteries that have lasted different amounts of time. So if we work that out, the probability of it dying is 0.199 when we work that out. Cool. Everybody okay so far? It's kind of confusing, this question, but you got to think about it logically. And the last bit is then going to be a hypothesis test. Right, so we're testing the sample means. So we'll start with our hypotheses. So H0, she believes the mean is more than 18, so we're going to go mu is 18, H1 mu is greater than 18. Cool. So her sample mean distribution, L with a bar over it, is going to be normal with a mean of 18 and a standard deviation of 4 squared divided by her sample size, which is 20. So that's our sample mean distribution. So just to summarize what we're going to do, we're going to do a normal distribution of the sample means. We're going to try and find the critical, is it two-tailed? No, it's one-tailed. So we're going to try and find this critical region. We know the significance is 5%, so 0.05. Find this critical value and see whether the mean of her sample, 19.2, is in the critical region or outside the critical region. So if we bring back the calculator, come on, see. And this time we're going inverse normal. Tail to the right, area 0.05. Sigma is going to be 4 divided by the square root of the sample size, which was 20. And mu is still 18. So we get 19.47 is our critical value. Okay. So that's our critical value. The value she got at 19.2, which is just below it, so it's not critical. So we'll say 19.2 is less than 19.47. Therefore, not critical. Therefore, the lifetime, or therefore evidence for this to catch up. So not critical. So we're going to accept H naught and say no evidence to suggest the mean is more than 18. Cool. All right. Anyone got any questions? That one's pretty tricky, but it was worth quite a lot of marks. You had quite a lot of time. Yeah. Cool. All right, we're going to move on. So we got 14 minutes. We'll try and get through one more question, which is this mechanics one. 6 marks. Yeah, that sounds doable. So, mechanics question. This is a vector question with some calculus. See how you guys get on. So 6 minutes to try this one. There you go. Great. Sorry, guys. I keep doing this. Yes, it was, wasn't it? Yeah, so we're going to integrate this. We want to go from a velocity to a displacement so that we can find the displacement of two things from each other, so that we can find the distance between the two things. So we, yeah, integrate it as I have done there, and I've put plus c on the end. Now, with plus c, bit weird with this one. Normally, if you put plus c, you'd want to try and find where plus c was, and that would tell you the. Okay, if we find plus c, we will then find the position vector of A and the position vector of B. We don't want that. All we want is the distance between A and B. So we don't really care where A and B are. We only care how they are relative to one another. Does that make sense? So if we found plus C would basically be our initial displacement. So if I imagine putting 0 in, the t equals 0 to find the initial location, we'd get r equals c. So my initial displacement is plus c. But I don't care about where we started. All I care about is A to B. So we're going to get rid of plus C and just not bother with it. Because all that will mean is our points aren't relative to an origin, but we don't care if they're relative to an origin because we're just trying to find out what's going on between them. Okay, so I'm going to put in T is 1. So our A will be 2i minus 2j. So as a column, it'll be 2 minus 2. Same thing for B, RB. We're putting in 4 this time, so we're going to get 2 lots of 2, which is 4. And vertically, 4 squared 16 times 2 is minus 32. So those are my vectors of A and B. No, we don't know that T is 1, S is 0. And we don't know it started at the origin. But it wouldn't matter anyway. Okay, so we worked out my two vectors. To find the distance between those two, I'm just going to subtract one vector, take the other. You can imagine it's like the whole vector triangle law. To go from A to B, I'm going to do subtract one of them. So if we do RB take RA, we get the displacement to get from A to B would be B minus A, so we're going to get 2 and then minus 30. So the distance between them would be 2 squared plus minus 30 squared square rooted. We'll finish this and then I'll have a look at the chat and see what you guys are saying. There might be a way to do it that way. So if we square those, square root them, we should get that distance is going to be root 904 meters. Or we could say it's 2 root 226 meters. So what was your, talk me through your plan then, Lucas. Well, I think I can guess what you did. Did you say it's starting at A, it's going to B, if it normally takes, if it's taking 3 seconds to go from A to B, you used A as the starting vector and B is somewhere it got to 3 seconds later. Is that right? So did you use T as 1? No, you didn't. What did you do? Yeah, you used T as 1, found plus C, and then put in T as 4 into your whole equation. Yeah, that's fine. That will work. Do you know S is 0 at A? I don't think you do. Oh, because you're starting at A. Okay, yeah, that's fine as long as you used... Yeah, okay. It's another way of thinking about it, but that will work as well. Cool. All right, that brings us up to the end. One thing I would like you guys to do: could you go onto Moodle and there's a college survey, and you need to do some survey responses on all of your lecturers. So if you guys could go on there, I think a few of you have responded, but yeah, you need to go and do student feedback of teaching, and also if any more of you want your mechanics results, send me a message on Google Microsoft Teams. And it's a distance. Yeah, it's a distance because we found the size of it. It was a displacement here, this bit here, this bit here was a displacement. The bit and then sorry, no, this wasn't a displacement. 2 minus 30 was a displacement, and then we turned it into this, which is a distance because it's the size of a displacement. Cool. All right. I got to go because I'm teaching again right now. But if you got any questions, quickly shoot them off. But better get on with my first year lecture. Cool. Have a nice weekend. Chat to you guys next week. Make sure you're uploading assignments and doing revision as well, because it's still kind of important. All right. See ya.